Moving on to problem 2. Given the linear system, determine whether the system of equations is consistent or inconsistent. If consistent, how many solutions does it have? So it doesn't tell us what method to use for this problem. But if we're talking about determining whether or not a system of equations is consistent or inconsistent, the best way or the easiest way to go about doing this is to use Gauss elimination. So I'm going to go ahead and write my augmented matrix. 1, 1, negative 1, negative 1. This should be second hand or second nature to you guys. You should be able to get easy points by writing the augmented matrix. So I need to go ahead and get it into REF. So I'm going to go ahead and make that a 0 and that a 0. So I'm going to say row 1 or row 2 equals row 2 minus row 1. I'm going to write my math over here on the side. 1 minus 1, 0 minus 1, 1 minus negative 1, 3 minus negative 1. And I'm going to say row 3 equals row 3 minus 3 row 1. So 3 minus 3, 2 minus 3, negative 1 minus negative 3, and then 1 minus negative 3. So when I do that, row 1 doesn't change. Row 2 becomes 0, negative 1, 2, 4. Row 3 becomes 0, negative 1, 2, and 4. And automatically we can see that 2 of my rows here ended up being the same, so I can stop here and I can say my system is consistent and infinite solutions. If I continue through, I can say row 3 equals row 3 minus row 2, and I can see my zeros fall out of the bottom. But I don't technically need to do this step. I don't technically need to do that step because I know that's going to happen. It didn't tell me to find it in REF, it just said determine whether or not the system is consistent or inconsistent. If it told you to go all the way to REF, you would have to do this last step, but I don't have to because I know that's going to be zeros. It's zeros all the way across. This will also be a 0, which means my system is going to be consistent and it's going to have infinite solutions. If this number here was not a 0, if it was a 1, then it would be inconsistent and have no solutions. Okay, so then part A is done. Part B, if the system has a solution, determine that solution. So I can go ahead, I can use back substitution, or I can go ahead and get into REF by getting one more 0. So I can go ahead and make that one a 0 by saying row 1 equals row 1 plus row 2. So row 1 becomes 1, 0, positive 1, and 3. And flip those. Okay, let me check my answers. So then this tells me that x1 equals 3 minus x3. And this one tells me that x2 equals negative 4 plus 2x3. So x3 is a free parameter, which means my solution is going to look like this. 3 minus t, negative 4 plus 2t, and then t. Yep. Okay, so there's my solution. Once again, you could have used back substitution. That's totally fine. If I have an infinite number of solutions, my preference is to get to REF, especially since I only had to do one more row operation. It just made my life a little bit easier because then I didn't have to do substitution to solve for something else. But note, x3 is our free parameter. It's an infinite number of solutions. If I pick a number for x3, I can solve for my other two. So infinite number of solutions, but they're confined to that relationship. So that's B. And then C, verify your solution. So here's my solution, so I'm going to go ahead and plug it into my systems. It doesn't say how many times to verify the solution, but let's pick equation 1. So equation 1, x1 is 3 minus t plus x2, negative 4 plus 2t, minus t equals negative 1. For equation 2, it would be 3 minus t plus t equals 3. I can see that's obviously true. 3 minus t plus 2, negative 4 plus 2t, minus x3 equals 1. So then I would go ahead and just solve for this. So this would be 3 minus t minus 4 plus 2t minus t equals 1. Or I can see it's -1 plus t minus t equals 1, -1. So I can see -1 equals -1. Forgot to transfer this negative over. So that one's good. This one says 3 minus t plus t equals 3. That's obviously good. And then this one says 9 minus 3t minus 8 plus 4t minus t equals 1. So 3t, so those cancel. That gives me 1. That one's true as well. Okay, so just verify by plugging it into your system of equations, and you can see whether or not you got the right answer. The second problem for problem 2 looks like this. Given the following system of equations, determine the following values. So here I have unknowns in my coefficients. And once again, it doesn't really tell us which method we're going to use. It just says find these values such that the inverse of A looks like that. That should be there. And find a value for B1 so that x2 is -6. So if we're looking for inverses, that means that we're either going to do A next to identity to go ahead and do identity next to A inverse, or we're going to do cofactors. For this one, it's going to be easier if we use cofactors because we're looking for individual elements, and I don't really want to do row operations if I can help it on an A matrix with these unknown coefficients, whereas with I do cofactors, I can do things individually and do things separately. So let me go ahead and write my A matrix, 3, A1, 2, 3, 1, 1, A2, 3, A3, 1, 5, and 3. So I'm going to go ahead, this is my A matrix, or my A inverse. So I'm going to go ahead and look at, okay, so this is going to be my cofactors transpose, because my determinant here is 1. My determinant of A equals 1. My cofactors here are transposed. So if I look at cofactor 3, or down here, cofactor 3, 3. If I remove the row, remove the column, I'm left with plus, that's a plus sign down there for the cofactor sign, 3, 1, A, 1, 2, 1. So if this is cofactor 3, 3 in A, then that means it's going to be this number here in my cofactors. So I have 3 minus A1, 2, that should equal -1. So that means A1, 2 is going to be 2. There we go, I solved for 1. So then I'm going to go ahead and pick another cofactor to find. So that one's done. So now I want to go ahead and pick this cofactor. So remove the row, remove the column it's in. So C1, 1 equals plus 1, 5, A2, 3, and 3. So that's going to be 3 minus 5, A2, 3, and that should equal this one, -2. So -5, A2, 3 equals -5, A2, 3 equals 1. There we go. I finished that one. Last one, I want to find this one, which means let's do this cofactor. Remove the row, remove the column. You can see the cofactors I'm picking give me my submatrix here, my submatrix there. So it only has one of my unknowns. So here I have cofactor 3, 2, and that's going to be a minus sign out front. And I have 3, 1, 3, A2, 3. And if that's cofactor 3, 2, that means it's 2, 3 in this matrix. So 2, 3 in that matrix. So that should equal 0. So negative 3A2, 3 minus 3 equals 0. So that means A2, 3 should equal 1. Just checking my answers over here on the side. Ah, did I ever find that one? Ah, I picked the wrong one. I thought that was weird. I found this one. Oh, bad. Okay, so just ignore the last, 3 minutes of the video. So now I want to go ahead and find this one. There we go. So to do that, I'm going to go ahead and pick this number. There we go. C22. Remove the row, remove the column. That's going to be a minus. In the middle there, it's plus, minus. Nope, it's going to be a plus. It's going to be a plus. So I have 3, A, 3, 1, 3, and 3. So the cofactors I'm picking still only have one unknown in each one. Just so happens you pick the right unknown. Okay, so that's 3, no, that's 9. 9 minus 3A, 3, 1. And that should equal this number here in my cofactor matrix. Equals negative 3. So that means negative 3A3 equals negative 12. C31. Just checking my answers. Yeah, A31. There we go. A31 equals 4. Okay, there we go. I found all my values. So then it says find a value for B1 so that x2 is negative 6. x2, according to Kramer's rule, if we're only looking at one individual x value at a time, that means x2 is the determinant of a2 over the determinant of a. We already know the determinant of a is 1, so I need to go ahead and find the determinant of a2. If I want to put a2 together, a2 is going to look like a. And now I know all the values of a. 3, 1, 4. And then the third column is 3, 1, 3. And then column 2 is my b vector, which is b1, negative 1, negative 12. So now I want to go ahead and find the determinant of this so that a21 equals negative 6. If the determinant of a is 1, that means the determinant of a2 should equal negative 6. You can find your determinant using any method that you would like. Does not matter. I will do cofactor expansion on row 1, just because then B1 only shows up once. So it's going to be plus 3 times this matrix, negative 1, negative 12, 1, 3, minus B1 times this matrix, 1, 4, 1, 3, plus 3 times this matrix, 1, 4, negative 1, negative 12. And that should equal negative 6. So that means I have 3, negative 3 minus negative 12, minus B1, 3 minus 4, plus 3, negative 12 minus negative 4 equals negative 6. That's 9. That's negative 8. So 3 times 9 is 27. That's negative 1, so plus B1 minus 3 times negative 8 is negative 24 equals negative 6. B1 plus 3 equals negative 6. B1 should be negative 9. I can go ahead and verify my solutions to all of this. I can plug it in, make sure everything works out. There's various ways. I can go ahead and I can take A. So if I find A times A inverse, it gives me A inverse. That should give me identity. So I can check all my values in A to get identity. I could have used that in order to solve for my values as well. There's multiple ways you can do this problem. So we can go ahead and verify our solutions, but I'm not going to do that. You can do that if you have extra time, but I am not going to. We can see all of our answers.